This is a problem on average normal stress, and it's actually kind of an inverse problem, sort of a design problem, because we have to figure out the position of a particular force to make some average normal stress parameters equal. It says that the uniform beam is supported by two rods, A, B, and CD, that have cross-sectional areas of 12 millimeters squared and 8 millimeters squared, respectively. Determine the position D of the 6 kilonewton load such that the average normal stress in each rod is the same. So let me write down some factual information. The cross-sectional area is 12 millimeters squared for AB. A is 8 millimeters squared for CD. We've got the 6 kilonewton force, and what we're trying to find here is this parameter D. And the thing that's going to tell us what the parameter D is when sigma average AB equals sigma average in CD. So we have to find D that makes that true. How are we going to do that? Well, let's develop an approach. The first step we're going to do is to do a free body diagram of the structure. And the idea here is that we want to figure out what the forces in the rods are. So we're going to look for FAB and FCD. The idea being that if we're going to calculate stresses, of course, first we have to know the forces. The next thing we're going to do is we are going to use the equations we get out of step 1, and we're going to put them into the stress equations where we equate the stresses as we've written here, sigma average AB equals to sigma average CD. And from there, we're going to be able to solve directly for what this parameter D actually is. Let's go ahead and get started. So number 1 is an FBD of the structure. Let me go ahead and draw this. Here is our beam. We've got FAB, FCD. We've got the 6 kilonewton force. And then we've got this distance D, which we are not, which is not known at the moment. We put a coordinate system, say X and Y, and you can see what's going to happen here. Some of the forces in the X to the right is positive, is equal to 0. There's no externally applied load in the X direction. Some of the forces in the Y, upward being positive, we get FAB plus FCD. 6 kilonewtons equals to 0. So FAB plus FCD equals to 6 kilonewtons. And then we have a moment equation. Now I'm going to take the moments around A, counterclockwise direction being positive. Just as a reminder, there's point A. What we get here is FCD acting at a moment arm of 3 meters minus 6 kilonewtons, the applied load, acting at a moment arm of D equals to 0. So what we get here is FCD is equal to 6D over 3. That's equal to 2D. Now let me emphasize that that's a numerical equivalence. The units obviously aren't the same. FCD has units of something like newtons or kilonewtons, and D is going to have units of something like meters. So there are some units there that aren't exactly shown in this equation. But what we have been able to do is isolate one of the forces in terms of the numerical value of D. Now, what we've got here is a way to then substitute this back into that equation, and we can write FAB similarly in terms of D, and what that turns out to be is 6 minus 2D. Now again, FAB obviously has units of something like kilonewtons. D has units of meters, so there are some units that aren't exactly shown in that equation. But the numerical values are going to be related as shown here. So now we know FCD and FAB, both of them, in terms of this unknown parameter D. From this step, we can't really solve for any of them. We've got 3 unknowns. We've only got 2 equations here. So we can't get to the end of the problem just with this part of the problem alone. We need another set of equations. And that set of equations is going to be the stress equivalence in AB and CD, as we'll see next. So here we're going to equate the stresses. And the way we're going to do that is just write the average normal stress equations. So if you remember, we can write something like sigma average equals to FAB over the area AB, and we want that to be equal to FCD over the area of CD. So let me go ahead and put in the numbers that we have here. FAB was 6 minus 2D, and this was going to be over 12 millimeters squared. And let me go ahead and write that as 12 times 10 to the minus 6 meters squared. And that's going to be equal to FCD, which was 2D, over 8 times 10 to the minus 6 meters squared. Okay. Now you can see that the 12 and the 8, even though they're times 10 to the minus 6, they just sort of cancel and become a 3/2. So we end up with a 6 minus 2D is equal to 2D times 3/2. And if we go ahead and do the algebra, we end up with 6 minus 2D is equal to 3D. That implies 6 equals to 5D, or D equals to 1.2 meters. And there's your answer for D. Now, as a check, let me flip the page and go ahead and plug in that value of D and figure out FCD is equal to 2.4 kilonewtons, and FAB is equal to 3.6 kilonewtons. So clearly those two add up to 6 kilonewtons. And then we can do a sigma average calculation. If we go through the calculation, the average stress is about 300 megapascals in each rod. So let's review for a moment. We had a problem in which we had kind of an inverse question, which was, where does this 6 kilonewton force have to be located such that the average stress in the two rods is going to be the same? And the difficulty here, the challenge, was that the two rods had different cross-sectional areas, so we couldn't just go straight away and assume that the forces were going to be somehow distributed equally in the two rods. But the approach was pretty straightforward. We had to draw a free body diagram of the structure, which is what we usually have to do in these kinds of problems, and then we had to equate the stresses. What we found out was that when we did the free body diagram, we were going to write the forces in terms of this unknown parameter D, and we ended up with these two expressions right here. And again, let me emphasize that the units there don't appear to work out, but there are some hidden units in that problem. F obviously has units of something like kilonewtons, D has units of meters, as we saw. So there are some units onto the numbers like 6 and 2 that are going to make the units for the equation work out correctly. After that, we equated the two stresses in the two rods, and we solved for D. And then finally, we went back and checked and made sure that both of the forces add up to 6 kilonewtons and that the average stresses that we calculate in the two rods are the same.